Well, what are some characteristics of polynomial functions? I want to start by showing you this quadratic that we have graphed right here. This is the function f of x is equal to x squared. It's one that we're used to seeing, and you can see that I have the function here centered at the origin. Now, watch what happens when I graph f of x is equal to x to the fourth. That's the green line that you saw appear there. And the shape of the function is going to be the same, and it's still centered at the origin down here. Now watch what happens when I graph x to the eighth, which is the red line that just appeared. So the shape of the function, again, is going to be similar in shape to the one that I started with, the one that was x squared, the blue line. But I hope what you're starting to notice about these functions is as the power of my function increased from a 2 to a 4 to an 8, the actual picture of the function became closer and closer to the y-axis, or it squished in. It kind of got squeezed in towards the y-axis. Okay, so it got steeper in its appearance. Now, another characteristic I want you to notice in this function is look at what's happening down here along the y-axis. And I'm going to change pictures for just a second. So here I am in the notes, and I wanted you to just be able to see, this is the function. I still have, they're different colors, but I have an x squared here, I have an x to the fourth here, and an x to the eighth here. But what's happening down here around the origin? Notice that my function is starting to flatten out as the power of my function increases. So it gets flatter around the origin in between negative and positive 1. All of these functions are passing through the same point, but it does, some of the characteristics would be that we're getting closer and closer to the y-axis, or we're getting squished in. We are flattening out here between negative and positive 1. And then another characteristic I want you to notice is, what do you see on the exponents here for all of the functions that I've graphed? All of these functions are even powered functions, and they all have the same shape here on our graph. What do you also see about the end behavior of my graphs? All of these even powered functions are moving off to infinity in the same direction. So they move off to positive infinity on the left hand side as well as on the right hand side. And by the way, that brings me up to another point, they are symmetric around the y-axis, right? If I flipped it over, if I folded the graph over along the y-axis, it would be symmetric on the left and the right. Okay, so what have we got here? Even powered functions are symmetric along about the y-axis. Their end behaviors are in the same direction, and in this particular case they're going to positive infinity. If for some reason my leading coefficient was negative, they would be moving off in the negative direction, but both ends would be moving in the same direction. Again, that's the characteristic. And so over here I have that summarized for you. Even functions are symmetric. The domain of the function, let's talk about that for a second. The domain of the function is all real numbers, and the range of the function has to do with the minimum value of the function. Okay, now let's look at, so those are the even powered functions. Now let's look at another set of functions. Okay, I'm back here in Desmos, and I'm going to look at another set of polynomial functions. The first one I'm going to start with is x cubed. Notice that my x cubed function, which is graphed here in red, comes up from the left-hand side, scooches over, and goes off to the right-hand side. So it comes up from the third quadrant and moves off into the first quadrant. Now, when I graph x to the fifth, I still have a same shape, a similar shape for x to the fifth power. It's just kind of starting to creep in a little closer to the y-axis. And then when I graph x to the ninth, which is the green line that just appeared on your screen, it is again similar in shape, but still closer to the y-axis. So here we have all three of these functions. Let's go back to our notes now. So if we wanted to talk about the characteristics of these graphs that we have, the functions that we have, we note that they are all the same shape, and that as the power of my function is increasing and getting larger, then the function itself is getting narrower and narrower. Around the origin, we have the same thing happening as with our even functions. The function here, the three that I'm looking at here, are actually flattening out again in between that negative and positive 1. And so what can we say then about this function? Notice that the exponents for all three of the functions that I graphed in this case are odd. So these are going to be the characteristics of odd functions. And what can we say about the end behavior of my odd functions? They're going off to infinity in opposite directions. So here on the left-hand side of this function, we're going to negative infinity, and on the right-hand side we go to positive infinity. So it's opposite in its direction. This is, in fact, the leading coefficient will be positive here, and so this is a positive function. If the leading coefficients were negative, then my function would just do this. Still, the end behaviors would be in opposite directions, so that characteristic holds for odd functions. The domain for this function, all the possible x values would be from negative to positive infinity, and the range on my odd functions is also from negative to positive infinity. Now what about symmetry? Symmetry on this type of a function is symmetric around the origin. And how we can identify that is symmetry around the origin is basically if I were to rotate around the origin, the point that's here in the first quadrant would rotate and be the same point down here in the third quadrant. So the symmetry around the origin looks like that. Okay, and these are characteristics of what we call an odd function. Now, let's go down here and look at this set of graphs that I have here. If I wanted to talk about this polynomial function right here, the end behavior of this function is opposite in its direction, so we could say that this would be an odd function, a positive odd function, because it's coming from the left, scooting over and going to the right. But another characteristic that we're going to define for our polynomial functions is that they are smooth and continuous. So you notice that this function is smooth in its curves and it is continuous. Just like this second graph we have over here, the end behavior on this function is going in the same direction and they're going positive, so this would be an even function. And you notice that this again is a smooth and continuous curve. Contrast that with these two pictures that I have here. These are not polynomial functions. They are discontinuous. They are not smooth at all. The curves or the graph itself has sharp corners. So these are not polynomial functions. In other words, for a graph to be smooth and continuous, it is another characteristic of our polynomial functions.